It matters.
All right, kinematics, here we go. Okay, let's say that we've got a ramp here, and we've got a little cart here, and we've got a motion detector here. The motion detector puts out sound waves right there, okay? And the cart is at the top of the ramp. Assume the ramp is stable and sturdy and steady, and only the cart will move. Okay, will you please sketch for me, what will the x versus t graph look like? Assuming that x is in this direction, right? Concave up. Straight curve, curvy up.
Yeah.
Curvy up. Like something like this.
Yeah.
Does it look good? Where will it begin? What's the y-intercept? Yeah, whatever this is, right?
Yeah.
That's x naught, okay? So whatever that is, that shows up here, right? X naught. Why is it not this graph?
Because
Okay, sketch the arrangement of those three devices so it would look like the green line. Actually, there's more than one correct answer. There's more than one way to get this accomplished.
I like Alex's way. It's the bumpy one. It's like extreme. It's like
Alex used extreme friction. So Alex, all you did, see, I was thinking about the same thing. Now I said use only these three devices. I was thinking what you could do is just put something here that'll keep it from moving, right? Yeah. You could do this. Yeah, put the motion detector there. You could do that. I was thinking this originally, motion detector here and just sitting. That'll work.
Put the motion detector on the car.
You could do
Like pointed at me.
maybe. You could do this with your motion detector here, so it blocks it. I guess that would work. Hey, I like that idea though. Could you do this? Could you just attach the motion detector to the cart and let it go? Would that make the green line?
It depends.
They don't move.
Yeah, relative to the motion detector, does the cart move?
No.
No, that's the whole thing about relativity. The whole thing that Einstein realized is that motion is relative. And so what you observe for motion depends just on what you're doing and what it's doing, and the motion relative between the two. Okay? We make an assumption all the time that we're an outside observer looking at it, and that we're this magical observer that's stationary in space. And as far as we know, there's really no place like that. And even if there was, I guess, we wouldn't know where it is, because we can't tell what's not moving because we're moving. All right. Okay. Well, how could we get the graph to look like this then?
You just push the car. I mean, it's going to be having going towards without friction.
That's just
Okay, we're going to have to assume no friction, right?
Yeah.
So that we can get constant velocity motion, right? So we're going to have like the motion detector here, and then we're going to have to give it a push, and then after the push, it ought to look like this, right? But before the push, it might look like something like this, x versus t. It's sitting there before the push. You give it a push, and then it goes, right? So you have three sections, where it's sitting still, where you accelerate it, and then where you stop accelerating it, and it just continues to go at the same velocity. Now, how do I know, when you're just looking at a graph, that this velocity is 0, this velocity is changing, or that's also called acceleration. This is accelerating with a positive acceleration, and this has a velocity that's constant.
derivative.
Could it slope?
Yeah, and you remember this from calculus, there are calculus tie-in here. It's the slope, right, of the first derivative of the displacement equation. First derivative of the displacement equation is velocity. Or, from the graph, it's the slope, right? So slope here is 0, slope here is changing. Okay, so we will actually be able to handle this part right here that we're not able to do last year. Because last year, everything was a constant acceleration. So we're going to have changing acceleration sometimes. But don't let that freak you out, because you already know your calculus. Right?
Yeah.
Right.
Yeah.
All right, that's okay. By the way, how was the derivative worksheet stuff? We okay with it? A little rusty?
Yeah.
All right.
But mostly because I don't want
Hey, every year I'm rusty at it. I just don't use it that much. And when you don't use it, you don't really lose it per se, but it takes a little while to bring it back up in your memories, okay? All right, and this slope is constant, so it's a constant velocity. So there we go. All right, so we got that going for us. Okay, we already talked about our calculus tie-in. We'll be using a lot of calculus this year. Well, I say a lot. We try to avoid calculus if we don't have to, unless it just makes the problem easier. And for some problems, it's just easier to use it. For some problems, it's necessary to use it. Okay? So here we go. Let's just do this. We have displacement, velocity, and acceleration. Okay? Remember that displacement is just where you're at. Okay? Velocity tells you, what does velocity tell you? Change in speed, or change in location, technically, right? Which tells you how you're moving and in what direction, right? How the object's moving and in what direction. How fast and what direction. And the acceleration only tells you one thing. How that one changes, right? So this is dx dt, first derivative of this equation, and acceleration is dv dt, which is technically d squared x dt squared, right? Double second derivative of the displacement equation, all right? Okay, and you can work backwards with your integral, correcto? All right. Okay, how are we doing? We doing okay? Yeah. Because I'm just moving along at a nice little clip that would take us a long time in physics. Actually, in pre-AP, this would be like a week already. All right, so let's see here. If you have a ball and you drop it, okay, what will the x versus t graph, the v versus t graph, and the acceleration versus time graph look like? Okay, I want you to sketch all three. Make sure your neighbor agrees with you. Okay? We're going to do a lot more of making sure that we work with with the peoples around you. There's actually 2 acceptable answers for each one. 2 that I can think of that are acceptable. Which one's easiest?
Acceleration.
Depends on how you think.
Yeah, it really depends on how you think about it. A lot of times, the acceleration is the easiest one, because when an object drops without air resistance, by the way, we'll do air resistance in this class.
Okay.
That'll take some calculus.
Lovely.
All right, when it drops without air resistance, what's the acceleration?
Constant.
It's constant at 9.8 meters per second squared, or 9.8 meters per second every second. So it will increase in speed almost 10 meters per second every second. Okay? So that means if there's no air resistance, you only have to fall a pretty short distance, or for about 4 to 5 seconds, until you're going 100 miles an hour. Okay? Which is pretty quick. Yeah, which is really weird. The thing is like if you jump off of a 4-story building, you'll probably hit before you get to 100 miles an hour, right? You won't be up in the air 4 seconds. 1001, 1002, 1003, 1004. You're actually going 1001, 1002, and you've sped up as you go, right? So it's falling 4 seconds is a long time. Yeah, if you're counting on the way down, you get to 4, forget about it. Forget about it. All right, so like that, right? Now we've made an assumption. What's our assumption? Yeah, we've assumed down is positive, okay? Now, if you don't assume down is positive, then your graph will look like this, okay? At negative 9.8. All right, so what's our velocity look like? Okay, where does it begin? Okay, if it begins at 0, what are you assuming? That you're holding it at x equals 0. Okay, if you call that x equals 0, and this is some other place called x down here, then it would look like this, okay? With the slope being 9.8 meters per second squared, okay? Is the slope. Okay, if you assumed up as positive, then you probably assumed this as 0, and this is what x. So your graph would look just the opposite, like this probably. Started up here in the air, ended at some other place. No.
No.
That's not what it would look like. What did I do wrong?
You started with the
initial
velocity.
Ah, yes. I'm thinking displacement, right? We would just start like that, right? Does that look better?
Yes.
Okay. So we still started at 0 velocity, right? Still started 0 velocity. All right. Now here we go. What do they look like over here?
Quadratic.
This one starts at 0 going up. All right. And here's what I was getting at. If you call up positive, then you probably call this 0, and this is x up here, and so it would be the opposite. Here's where we're going. It would look like that. Okay? Does that make sense? I had jumped one step ahead of myself.
Yeah, that makes sense. Yeah.
All right, so there you go. All right, now here's the deal. For constant acceleration then, what's the equation of this graph? In math class.
X squared.
It's a quadratic with an x squared in it, right? It's y equals, no, usually you do this. X equals a, no. It's usually y equals ax squared plus bx plus c, right?
Yes.
Okay, for us, it will be x equals x naught plus b naught t plus 1/2 at squared, where there's that term, there's that term, there's that term, right? Okay, so that's why it turns out to be this equation, because it's quadratic. Okay, so our first equation actually just comes from, our first and constant acceleration equation just comes from that graph. Okay, it's quadratic. Okay, so this one, what's the equation of this graph?
Y equals mx plus b.
Y equals mx plus b, or in our terms, it will be instead
B naught plus
b
at.
equals b naught plus at, where that's your slope and that's your y-intercept, right? Our y-intercept, or our beginning velocity, was 0 in our case, right? So that's where those two come from. The equation for this one we never use. Actually, technically we do. It's the condition for using these two. Acceleration must be constant. It's just a number, okay? That number that doesn't change. If the acceleration is changing, these two equations will be of no use to us unless we have something like this, where we have a certain acceleration and then it drops to a new acceleration like that. Then what we can do is we will have a piecewise graph. So let's sketch what that would look like. If I have an acceleration graph that looks like that, what will the displacement and velocity graphs look like? X, T, here, let me draw it nicer. X, T, B, T, A, T. and this one I've got drawn like this, okay? Now we're assuming that this drops instantaneously. Now in the real world, and sometimes on tests, they'll ask you to sketch this, and you remember from last year, this is like a, kind of a smooth transition, right? But we'll assume it to occur over a very short period of time. So we have a positive acceleration here, and a smaller positive acceleration here, okay? And here's our break time, there, and there. Sketch what the velocity versus time, the acceleration versus, the displacement versus time will look like.
It should be a lot
Okay,
shorter.
don't be stumped. If you just had this graph, what would it look like? What would this and this look like? And then if you just had that graph, what would it look like? And then make sure the relationship between those two are appropriate. Like for instance, if this is flat or constant, then this has to be linear, and this has to be quadratic, right? So then you're going to have linear here and linear here, but they won't be the same linear, right?
Right.
You'll have quadratic here and quadratic here, but they won't be the same quadratic. Does that help out? So just break it down into stuff you know. Okay. Linear, right?
Right.
What kind of linear here?
Steve?
Steep because big slope, right? Do we know where it starts?
Well, we can
Zero.
say whatever. It's
Yes, because we're moving backwards, we're integrating, right?
right.
We're integrating to go backwards, and remember when you integrate to go backwards, that you need to know the initial condition, because otherwise it's that constant that sits out there at the end of the equation after your integration, right? Without the initial condition, you don't know what it is. So I'm going to assume it starts at a positive velocity, but it doesn't have to. It could start down here. So assuming it starts there at V0, then I'd have a slope like that. Positive slope. Okay, now how does this slope differ than that one?
It's less
It's
steep.
less steep.
It's just like that, right? It's still positive, but less. Okay? All right, so over here we got to have a quadratic. And once again, if we're integrating here and moving backwards, remember that's information we have to have, right? The initial condition. So just to mess you up, I'm going to make the initial condition here down here. Just to show you that it can be. Doesn't have to be, it just can be. If yours isn't here, that's fine. All right, so what's this one look like?
Quadratic.
Quadratic pointing which way?
Up.
Up, right? Because we have a positive acceleration. So I'm going to draw a quadratic up, but I'm going to do this. I'm going to draw like a parabola here, okay? There's, oops, you know what? I need to draw a steeple one, or it's going to look ugly. It's going to look ugly anyway, probably. So here's my quadratic here. You know what? If I started off with an initial velocity here, how do I represent that right here at time equals 0?
It's not flat.
So my parabola won't be like that, because if that's my parabola, the slope here is 0, right? So where does my parabola have to start? It has to start with a positive slope somewhere already, right? So this should really start the way I've drawn mine, with a slope already built in. Okay? Does that make sense? Now if you had yours start at 0, 0, then yours will start at this point of the parabola. Okay? Alright, so mine starts with a slope, it goes up like that, and so my parabola will go like that until I get to here. And then what's happened?
It's
Another
slope-
parabola.
the slope loss.
Okay, it's another parabola. Now, if I just look at this, follow this backwards to right there, this parabola would start with this velocity, right? Somewhere over here at time equals 0. So I'm going to start it right here, and it's going to should have a higher starting spot, higher slope to begin, but it's wider. So the green parabola is more like this, right? Because it has a smaller constant, but it starts farther out here. Does that make sense?
Yes.
Okay. Now it's going to be exceptionally hard to draw. I'm going to go like this. You know what? And I did a bad job. What's bad about mine?
Transition.
Because there's a parabola and there's a parabola, which is probably what a lot of you drew. But where's it wrong? It's the same.
No.
This goes downward, right?
Right.
This one will go down, and it looks to not be quite as steep. Something like that, maybe. Not quite as steep. Okay, this blue one stays the same over here, but the green one now is going to look
Concave down.
concave down. Now this is actually going to be a little easier for us. We're going to be concave down, but we're going to be starting with an initial velocity already, right? Initial velocity which way? Positive or negative?
Positive.
Okay, so here's the deal, everybody. The green parabola now must match up and have a smooth transition here, but on this parabola, where will I be beginning?
On the left side.
I'm starting with a positive velocity, which means a positive slope. So I'm starting somewhere over here on my parabola. You see how that makes for a nice smooth transition? Because it'll start right here, and then it will be a parabola like this, right? So here's my green parabola. It looks like that. So it'll transition nice and smooth between those two. Okay, see how that works?
That's hard.
That's purdy. All right. Okay, so if you have a piecemeal acceleration, where you have a constant acceleration which quickly changes to a new constant acceleration, essentially we can still use these equations, or we can solve it graphically. Some of you, this really appeals to you, the graphical method, because you see it and makes sense. That's great. Some of you are more algebra, your brain works more algebra based, which is fine. Then what you'll do in an algebra problem is, say if this is at 3 seconds, then you will split your problem up into starting at x0, moving to x3 with acceleration number 1. And then from x3 to x whenever, you'll have acceleration number 2. And the ending condition here becomes the initial condition here. Does that make sense? So you step through your problem piece by piece. Okay? All right. A problem like this a lot of times is they have a rocket. The rocket takes off. The rocket takes off with a certain acceleration from the ground. And then after a certain height or time, say time 3 seconds, the engine cuts out. And so you have a new acceleration. This acceleration would be negative 9.8 meters per second squared, because that's down. And this acceleration is positive because it's up. And then you could find out like how high it goes, but you'd have to find out from here to here where it's at and how fast it's going, right? You'd have to find x3 and v3 here, and those would be the initial conditions for this part of the problem, where you find out how high it goes and how long it takes to reach the top and that sort of thing. Okay? All right. So we could work one like that if you want to actually have one in here if you'd like to work one. You want to work one?
Yeah.
All right, let's do it. In fact, here we go. It's almost the exact same problem I've written already. The acceleration between here and here is 30 meters per second. After 3 seconds, it coasts to a stop someplace. I want to know the max height and the time to get there. Okay, so question 1 and question 2. All right? And go.
It's 3 seconds.
3 seconds of acceleration, and then the rocket motor cuts out. Okay? And they can add a whole nother part to this. They've done this on a problem before where it accelerates, rocket motor cuts out, coasts to a stop. When it gets to the top, the parachute comes out and floats down, so you have a new acceleration for the float down part. By the way, I'll head you off at the pass here. A lot of students will ask, does the 30 meters per second include the 9.8 of Earth? The answer to that is this is the acceleration. So you don't have to account for gravity. It's already, that's it, okay? That's the acceleration. All right?
Yeah.
That would be taken into account, like for instance, if we extended this to a force problem, you would have the mass of the rocket would be given, and you'd be given the thrust. But remember, if you draw a picture of the rocket, how many forces act on it? Assuming no drag. 2. They are the weight and the thrust, and F equals ma. The thrust minus the weight equals ma. And so this A will already have incorporated into it the G. Does that make sense? That will be, oops, where is it? Right there. Okay? So it's already incorporated into the problem because of the weight of the rocket. All right? To the max height, and what is the max height?
Yeah, that's right.
Now, some of you can solve it graphically if you want, and work backwards if you would like. In fact, some of you, if you really want to put that calculus to use, will do this. The acceleration equals 30 meters per second, but acceleration is dv dt, right? All right, so separate variables. dv equals 30 dt. Integrate from 0 initial velocity to v naught, from 0 time to t. So you set up your differential equation, put in your variables. So the left-hand side becomes, oops, sorry, from v naught, which happens to be 0, to v. So on the left-hand side, you get v equals 30 t, right?
What?
Yeah.
Plus.
Now,
Plus C.
no, I put a definite, what's that called? Definite integral, right? Okay. Now, by the way, everybody, don't be confused. Well, here, let's just do the next part then. So that tells you the velocity at any time from 0 to 3 seconds, right?
Right.
And then, all right, but v equals dx dt, which equals 30t, right? If I separate variables, dx equals 30t dt. Integrate, integrate, integrate. Where did I begin?
0.
0 height, I end up at x. Where did I begin in time? 0 to t. I'll just do t, and then you can plug in the 3 if you'd like. So this side becomes x equals, what's this become? 30t squared divided by 2, right? Which is 15t squared.
Yeah,
That's it, right? Okay, now, notice that v equals 30t and x equals 15t squared. This is good from 0 to 3t, right? Or 0 to 3 seconds, right?
Right.
Now, look at that. Here. X equals x naught plus v naught t plus 1/2 at squared. V equals v naught plus at. What's my initial velocity? 0. That's 30t. What's this? Start at 0, start at 0. X equals 1/2 30t, which is that, right? It's the same thing.
I got the, I got that.
Yeah, you get the exact same thing, right? So where is the object? See, most of you will just jump to this, right? I'm showing you the calculus because there'll be somewhere we need to use calculus. All right? Wait a minute, don't be frightened. Some of you are like, relax, relax. Okay, so at 3 seconds, where is the thing at? If I'm plugging in 3 here, where's it located?
135 meters.
135 meters. If I plug in 3 here, how fast is it going?
90.
90 meters per second. So here we go. I'm going to write those down right here. My velocity is 90 meters per second, and I'm looking at 135 meters. All right. I want to know how high it goes. I want to know where the heck is it up here. Okay? So how do I do that? How about x equals x naught plus v naught t plus 1/2 a t squared? Will that do it for me?
Yes.
Do I know enough? Do I know x naught? Actually, no, I don't know x naught. I know x3, right? And v3, right? Because those are my starting conditions now, correct? Okay, so x3 I know. That's 135. v3 I know, because that's 90 times t plus, minus.
1/2 9.8 squared. Yeah.
Uh-oh. Uh-oh, indeed.
Yeah.
There is nothing wrong with what I did. And you're going to do this all the time in this class. You're going to do nothing wrong, but still not get the answer. Because while you did nothing wrong, you just have too many unknowns. Okay? So we don't know the time. All right? Well, puns. Let's redo. V equals V naught plus AT. Oops. V3. So V at the top equals
0. Oh wait.
90
Oh wait, 90.
minus 9.8 T. Nothing wrong, just no answer. What do we do?
Well,
All the way at the top is going to be 0.
all the top is 0, so that
We
means
do know something here because this is the velocity at the top, right?
Yeah.
This is the top, but at the top we do know that the velocity is 0. So how long does it take to get there?
90 over 9.8.
90 divided by 9.8, which is
9.18.
9.1, just say 9.2 seconds.
Yeah.
Okay? Now wait a minute. Wait. Is that 9.2 seconds from here?
No, it's 9.2 seconds.
No, because 9.2
After-
Right, 9.2 seconds from here, right? So the answer to time to max height is not 9.2. It's the time from 0 to 3 plus the time to go from 3 to the top, right? Which gives us, what, 12.2 seconds, correct? 9.2 plus 3. Okay? Now, if I want to find when it gets to the top up here, what time do I put in here? Do I put in the 12.2 or the 9.2?
9.
Why can't I put in 12.2?
Because you're using different velocity.
Because I'm starting from 3 seconds, right? If I put in the 12.2, I'll get an answer. It'll just be wrong because this equation is not appropriate for the whole thing, right? So you're going to put that in there, and how far is it? Actually, from here out, it's just math, right? All the heavy horsepower we've already done, right? All the real work is done. So I'm just going to give you the answer. It's 5:48. Okay? All the real thinking is complete. All right. 548, sorry, 548 meters, which is a long way. That's what? Between 1,500 and 2,000 feet? That's pretty good. Now, it won't really go that high because of drag, right? Air resistance. But it will still go a long way. How many of you have shot model rockets off before? You've never done it before, you should. It's fun. It's fun.
You did? You went to the No, we didn't get to shoot my nose. Really? I mean, I shot like firework rockets.
In fact, my son's 9th birthday party, his last birthday party, we had a rocket party.
Yeah.
So we got all the old Estes rockets out, and we went to the park and shot off a whole bunch until it started to rain on us and we thought we were gonna get struck by lightning, so.
That day we had it on the head.
All right, x equals 3t to the 4th power minus 6t squared plus 2. Okay. Is the acceleration constant?
No.
Oh no, the acceleration is not constant. So wait a minute. At like time equals 10 seconds, how do I figure out the velocity at 10 seconds, or where it's at 10 seconds, or its acceleration at 10 seconds? How do I do that? One of these I can find right now. Which one?
X.
I just plug it in and solve it. Right? How do I find velocity? All right, will you please derivatize this for me?
12t cubed minus 12t.
See, this is great. This is why my calculus never gets any better. It's still rusty from college because all I say is, so what's the derivative of that? And then students go 12t to the 3rd power minus 12t. And I never have to work it out myself. All right. Okay, it is 12t to the 3rd power minus 12t. So then you'd plug that in. If you don't plug this in, what the heck? You're supposed to correct me when I do wrong things. I'm on tape. I'm going to be wrong forever then. That's not good. How do I find acceleration? Which is what?
36t squared minus 12.
See? I don't even know how to do these anymore. Because you do them all for me. Okay, there you go. That's how you figure out your displacement, velocity, acceleration at any point. Piece of cake. Well, what if it's the other way around? What if they give you the acceleration as negative 6t plus 2? And let's say that velocity naught is negative 8 meters per second. So it begins at negative 8 meters per second, and it begins at a location of 2 meters. All right, what's the velocity and displacement equation?
Negative 3t squared plus minus 8. Right?
You write it down.
You kind of superhero, Miss
That's my superpower. All right, negative 3t squared plus 2t minus 8, correct?
Yeah.
All right, what's x?
Negative t cubed
Plus t squared.
minus 8t plus.
All right, we got that? Okay, there are several on the e-homework that have to do with, asking certain things about these equations. Now, what if they'd ask you something like this instead? I'm sorry, about when it's not constant acceleration, okay? If you find an equation where the x equation is not squared, it's cubed or higher, or the velocity equation that's not linear, it's like squared or higher, then it's not a constant acceleration, and those equations that we've used, the constant acceleration equations, are of no use. You can solve it with that, you'll just get them all wrong. Okay? And then if this is not a number with no variables in it, then it's not constant. You got to use calculus. Okay? So I mean, it's a dead giveaway. Oh, quartic, no good. No quadratic. So we can't assume constant acceleration. All right. Now they could ask you questions like this. Well, what's the displacement of the object between 2 and 4 seconds? So what's the delta x between time 2 to 4 seconds? All right, 2 to 4 seconds. How do you solve that?
Absolutely.
Now, one way to do that is to take this equation, and when you integrate it, you just integrate it like this, from 2 to 4 seconds, negative 3t squared plus 2t, minus 8. Integrate it, definite integral, you'll end up with x, right? Right. The total x traveled, or the change in displacement. Now, that could come up to be 0 if they start and then come back, right? So don't get freaked out if it comes out to be 0. Or negative, that's all right. It just means it's either went negative the whole time or started positive and turned around, right? Okay, the other way to do that is if you just solve the equation like this, plug the number in for 2 and 4 and subtract them. But which one do you subtract? If I want to know delta x, that's between 2 to 4 seconds, then I have to have x at 4 seconds minus x at 2 seconds, right? Final minus initial. Take the 2 and subtract. That'll work as well. Okay? It's the exact same thing. And I have no idea what that answer is, I just threw it up there.
Oh.
Okay? Okay. Let's do this real quick. If this is velocity versus time, I'm sorry. If this is velocity versus time, and my graph looks like this, where this is an asymptote, where that's the terminal velocity, so you're a skydiver and you jump out of a plane, and that's your velocity versus time. Okay? All right. When you first jump out of the plane, what should your slope here be?
If I first jump out of the,
Negative 9 or positive.
Yeah, negative 9.8. 9.8 meters per second squared downward, right? So which way have I called positive?
Downward.
I've called down positive. The slope should start off at 9.8 meters per second squared. All right? Now, can you please attempt to sketch what will x versus time and acceleration versus time look like for that? Okay? Just a sketch.
So, okay, are we assuming that you'll reach terminal?
Yes, you reach a terminal velocity, at which time this will go on at a constant velocity infinitum. That's a college word for a really long time. Until splat. How about that?
Then does our velocity go to 0?
Yeah, then your velocity goes like that. It's one of those instantaneous acceleration drops from whatever our, well, actually on the acceleration book, it'll be 9.8, and then you'll have a big spike the other direction.
In a young growth.
Oh!